In the dark, one of these can come in very useful. It gives off light, but virtually no heat. Photons of visible light from atoms have energies of a few electron volts, a tiny amount of energy by everyday standards. On the other hand, nuclear processes have an energy scale of a few million electron volts. Why is there such a huge difference between atomic and nuclear energies? That's one problem, but things become even more puzzling when we look more closely at the radiation that atoms and nuclei emit. If ordinary white light is shone on a prism, we get a spectrum with a continuous range of wavelengths, all the colours of the rainbow. What we have here is a continuous spectrum of photon energies. The colour of the light changes gradually with energy. At the red end here, the photons have energies of about 1.8 electron volts. And moving across to the violet end, the photon energies are higher, around 3 electron volts. Now, if we transfer energy to an atom, it can lose its excess energy by giving out radiation. And it's natural to expect that this radiation will always have a continuous range of wavelengths. But in practice, it's not as simple as that. For example, this represents the visible spectrum of copper. No light at all is given out in some regions, but there are sharply defined lines. They're called spectral lines, and they show that photons are given out with certain definite energies. Now, it turns out that the atoms of every element have a unique spectrum. It's the element's fingerprint, if you like. Now, it's important to remember that spectra aren't only in the visible range. Detectors other than the human eye show that radiation extends in both directions, through the infrared and through the ultraviolet regions. Now, copper's a pretty complex atom containing quite a few electrons all interacting with each other. We might expect that a simpler spectrum would occur for hydrogen, which after all has only a single electron. It turns out that in fact hydrogen has 4 spectral lines in the visible range, and the energies of these lines are a few electron volts, and that sets the scale for all atomic processes. When we look at nuclei, we find that they also emit spectral lines, but the gamma ray photons emitted have much higher energies. They're way off scale, certainly not visible. But for the moment, let's focus on the hydrogen atom. Why are these energies in the electron volt energy range? And why do these photons have definite values of energy?
Well, let's see if I can't find an answer to these questions. If we approach an atom, then all we see is a fuzzy ball, a cloud of electrons surrounding a central nucleus somewhere down in the middle there. And it's these electrons out here that are responsible for emitting the photons of the atomic spectrum. And then it's the neutrons and protons inside the nucleus which are responsible for giving out the invisible gamma rays of the nuclear spectrum. So the question is, why do these spectra have photons of only certain allowed energies? Now, I can answer that if I'm allowed to make an assumption, a big assumption. I want to assume that the electrons and the neutrons and protons exist with only certain allowed energies. Here I'm specifying just 4 of the allowed energies for the electron in a hydrogen atom. It can take on any of these values, but it is not allowed to take on anything intermediate. If it wants to change its energy, it must go in one instantaneous quantum leap from one allowed level to the other. And the energy difference between the levels appears as the energy of the emitted photon. The bigger the quantum leap, then the greater is to be the energy of the photon. Now, because there are only certain allowed values for the initial and final energies, there will only be certain permitted values for the energy difference, and so for the emitted photons. And because we know that the energies of the photons emitted by atomic hydrogen are just a few electron volts, then I need these spacings also to be separated by just a few electron volts. As for the nucleus, the nucleus of a more complicated atom than hydrogen, one with several neutrons and protons, I'm going to also have to assume that these neutrons and protons also only have certain energy values. But now the separation of those levels is going to be millions of electron volts. And that's necessary if I'm going to have the emitted photons as gamma rays. So that then is the bare bones of my explanation of the discrete nature of the atomic and nuclear spectrum. But of course, as it stands, it's not much of an explanation. After all, everything hinges on these particles having only certain energy values in the first place. And why on earth should that be so? To make further progress, I need to know more about the behavior of these particles, and particularly about how that behavior depends on energy.
That tube produces a beam of free electrons, which are aimed at a target of carbon, and this is the diffraction pattern produced. The more the electrons are accelerated, the higher their energy becomes, and so the smaller the diffraction pattern becomes. If we decrease the energy, the size of the pattern increases. We can only understand this pattern if the electron behaves as a travelling wave. The wave, of course, has a wavelength. It's called the de Broglie wavelength, lambda dB. The wavelength of free electrons can be changed continuously. As the electrons accelerate, their energy increases, their de Broglie wavelength gets shorter, and the pattern shrinks. Just like light waves, electron waves can be focused to produce magnified images. This is an image of an aphid taking in the sap from a leaf. It was taken with an electron microscope. And this is the head of an ant. This is far better resolution than we could ever achieve with an ordinary optical microscope, because the electron's wavelength is much less than the wavelength of light. The electrons are a much finer probe. The wave associated with the free electron, like one in an electron microscope, is rather like this. And I can adjust the wavelength pretty well how I like. Right, now suppose I were to fix one end here, like that. What do you think will happen now? If I shake this end correctly, I can set up a standing wave. There we are. There are a definite number of half wavelengths between the ends. Now, I think you'll see a standing wave even more clearly with a continuous piece of string, like this. It's fixed at both ends, and one end is being shaken at just the right frequency to set up 4 half wavelengths between the ends. And there's 3 points, like this, where the string is not moving at all. Now, if we turn the frequency down, get it just right, there we are, there's 3 half wavelengths between the ends, and now only 2 points are stationary. Down again, 2 half wavelengths between the ends, and now the middle is stationary. And again. Right, well, this is the lowest frequency standing wave on this particular piece of string. There's 1 half wavelength between the ends. The key idea here is that every standing wave has a whole number of half wavelengths between its ends. So what's all this got to do with electrons? Remember, a free electron is associated with a travelling wave. It's natural to expect standing waves to be associated with an electron that's confined. Imagine an electron, or any other particle, moving around between these 2 parallel plates. The particle's confined so that it can't escape. Let's go down between the plates and try to visualize the waves describing the particle. Each wave associated with the confined particle is a standing wave, like this one. Each standing wave has a whole number of half wavelengths between the boundaries. There's 3 in this case here. The number of half wavelengths is called the wave's quantum number. So the quantum number of this particular standing wave is 3. Now, because there are only certain definite numbers of half wavelengths between the ends, it's not surprising that the confined particle can only have certain definite values of energy, energy levels. Each energy level corresponds to a particular standing wave. This one corresponds to the lowest energy level. This one to the energy level above that, and this one to the energy level above that. So what happens when the energy of a particle changes? It makes a transition or a quantum leap to this level, and a photon is emitted with the energy exactly equal to the difference between the higher energy level and the lower one.
So that's how an electron behaves when confined between two parallel plates. Is there some way I can use that to help me with my understanding of the hydrogen atom? Well, in a hydrogen atom we get confinement of a sort. The electron's negative charge is attracted to the positive charge of the nucleus, and that means the electron tends to stay close to the nucleus. It behaves almost as though it were contained in a spherical three-dimensional enclosure. Now, actually, from a mathematical point of view, it would be simpler for me to deal with a cube rather than a hollow sphere. A cube is just three sets of parallel plates, and we've already dealt with an electron between one set of parallel plates. It's a very crude model. After all, atoms are not cube-shaped. But let's see how far I can get with just that. Now, an electron moving in 3 dimensions will have a wavelength associated with each of the 3 directions. And if the electron is in a box, then we shall have to fit in a whole number of half wavelengths in each of the directions between the walls of the cube. Now, here I've got a wave that's confined in the x direction between those 2 walls there. I can put in a second wave for the y direction like that. I'll put that in front like that so that it becomes superimposed. That's the situation for 2 dimensions. And then finally, a wave for the z direction, which is the direction along which you're looking. That goes in there. So that's the 3 waves superimposed, and it looks a bit of a muddle. So let me just show you what it looks like when the 3 waves are in the one box. There we are. With this particular case, I've got equal numbers of half wavelengths in all 3 directions. Now, that is not necessary. I can have different numbers. Here you will see I've got more waves in one direction than in another. In fact, I'm now going to need 3 quantum numbers to tell me how many half wavelengths I've got in each of those directions. 3, that is, instead of the 1 quantum number we had when there was just confinement between a single set of parallel plates. Now, corresponding to each combination of 3 quantum numbers, the electron in the box will have a certain energy. And the expression for that energy turns out to be this. This part here is, if you like, a basic unit of energy that essentially sets the scale. H is Planck's constant, m is the mass of the confined particle, and L is the length of the box. It measures the extent to which the particle is confined. And you see that because L is on the denominator, the smaller L is, the greater is the size of the energy unit. The expression in brackets gives us the 3 contributions from the 3 different directions. They involve the 3 quantum numbers, n1, n2, and n3. The lowest energy is when all the 3 n's are equal to 1. I then have to add together the 3 contributions, and this gives 3 basic units worth of energy. And here it is. The scale is in terms of that basic energy unit up there, and as you see, this level has got 3 of those units. The next one up, that corresponds to one of the n's taking the value 2, whilst the other 2 remain at 1. So in my expression, that gives me 2 squared plus 1 squared plus 1 squared, which is 4 plus 1 plus 1, which is 6, which is where I've got that level. And of course, you've got the other levels up there corresponding to the higher values of n. So straight away, my model of the wave confined to a box has produced the first important feature I was looking for, the discrete energy level nature of these energies here. I can go even further and reproduce the values of these energy levels. What I'm particularly interested in is not so much the absolute values as the spacings. It's the energy differences that give rise to the energies of the emitted photons. And as we see, these energy levels here are separated by a few times the basic energy unit. So what do we expect for the basic energy unit of the hydrogen atom? Well, L is the size of the box, so that will be typically the diameter of an atom. And the typical size of an atom can be determined from a picture like this. This photograph is actually showing an array of individual atoms taken with a type of electron microscope called a tunneling electron microscope. From such a picture, the typical size of an atom has been measured to be 5 times 10 to the minus 10 meters. So in terms of my model, that's what I'm going to take for my value of L. As for M, that is the mass of the electron, 9.1 times 10 to the minus 31 kilograms. So putting these values into our expression for the basic energy unit, what does that give us for the hydrogen atom? Well, the answer turns out to be 1.5 electron volts. And that's so close to an electron volt that we might just as well simplify our scale and write it in terms of electron volts. So this then is my prediction for the hydrogen atom.
By measuring the wavelengths of atomic hydrogen spectral lines, we can measure the spacings of hydrogen's energy levels. There you can see the energy levels gradually get closer together. The top one's about 13.6 electron volts above the bottom energy level down there. Now up here, the electron isn't confined at all, so it can have any energy it likes. So how well does these experimentally determined energy levels agree with the model? Well, we've aligned the bottom levels for comparison. And we can do that because we're only interested in the spacings, not in the absolute values of the energies. The lowest energy levels agree pretty well. The spacings agree to well within an order of magnitude. But up here, where the electron can have any energy, well, the agreement there really is pretty bad. So the model has broken down. The model doesn't appear to be very good then, does it?
I'll come off it. I think it's done pretty well considering. In the first place, it's reproduced these discrete energy levels, and that's a very important feature because that is the secret of understanding the discrete nature of the wavelengths of the atomic spectrum. Not only that, but as you say, the levels are of the right kind of order of magnitude for the lower ones. Fair enough, it does break down higher up, but that's only to be expected. After all, the atom is spherical, it's not cubical, and more important than that, it's got a fuzzy edge. Now, in my model, I had rigid boundary walls. You know, the electron could never get out regardless of its energy, so my energy levels go on indefinitely. Whereas with the electron in the atom, if it gets beyond a certain amount of energy, then it can actually escape from the nucleus, and the atom gets ionized. So the disagreement here is not at all surprising, and I know exactly what's wrong with the model, and if I wanted to, I could improve it. I could make it much more sophisticated. But rather than do that, what I'm more interested in doing is now taking up the challenge to use the same simple model to understand the spectrum given out by the nucleus, the tiny central core of the atom.
I wonder if you realise just how small the nucleus is. Suppose this empty studio represents the size of an atom. The electrons can be found anywhere in this entire volume. But the nucleus, where most of the mass of the atom is concentrated, that's situated somewhere in the middle. Here it is. Now, on the scale of the studio, the nucleus occupies about as much space, not of that pinhead, it's far too big, but of the very tip of the pin. So most of the atom is just empty space. That's quite a thought, isn't it? Everything around us, you and me, for the most part, we're just empty space. Now, bearing in mind just how small the nucleus is, it really is quite remarkable that we can arrange for two nuclei to collide. And yet nowadays, that's done routinely. In this experiment, the energy levels of magnesium nuclei are being measured by bombarding them with helium nuclei, which are normally called alpha particles. The alpha particles are accelerated by about 17 million volts, bent through 90 degrees by magnets, and then directed towards a thin piece of magnesium film. Experimenters can actually monitor the collisions between the tiny alpha particles and the magnesium nuclei. The stream of helium nuclei pass through the magnesium sample, and in some cases an alpha particle transfers some of its energy to a magnesium nucleus, which is then excited. A very short time later, the excited nucleus loses its excess energy by emitting a photon. It's by measuring the energies of photons like this that we can measure the spacings of the nuclear energy levels. This peak corresponds to the photons given off in the transition from the second lowest energy level to the lowest level. It has an energy of about 1.8 million electron volts.
The nucleus consists of neutrons and protons. These are confined to a small volume, the volume of the nucleus. I'm now going to apply my box model to this nucleus. Straight away, the confinement of the neutron and proton waves produces discrete energy levels. What of their spacing? This time I have to use the mass of a neutron or proton. That's about 1.7 times 10 to the minus 27 kilograms. As for the value of L, the size of the cube, I know from studies of collisions between nuclei that the size of a nucleus is about 10 to the minus 14 meters. Putting these new values into my expression for the basic energy unit, I get a unit for the nuclear energy scale of the order of millions of electron volts. Exactly what is required. Well, here once again is the atomic energy level diagram for hydrogen, measured in electron volts. For the nuclear spectrum, one would find that the lower energy levels would be separated by millions of electron volts. And on this scale, that would mean that the energy level diagram would have to break through the confines of this studio, and we would go soaring up high above the atmosphere to a height of several thousand kilometers. And this is where we would find the first few levels of the nuclear spectrum. And I reckon that my model has been very successful. Modeling atoms and nuclei as waves confined to a box gives discrete energy levels. And the mass of the particle and the size of the confinement gives the right order of magnitude for the spacings. Nor do I need to stop here with a study of the nucleus. I can continue my journey into the heart of matter and inquire what happens inside individual neutrons and protons. And there one discovers constituent particles called quarks. And they're confined within the volume of a neutron or proton. If I apply my box model to them, I find that the quarks have an energy separation which is to be measured in terms of thousands of millions of electron volts. And on this scale, that takes us soaring up far beyond the moon to a height of several million kilometers. So there we have it. The atomic spectrum, the nuclear spectrum, and now the subnuclear spectrum. They're very different from each other in terms of the magnitude of the energy scales. But throughout them all, the underlying physical principles remain the same.